The last video for today, I want to talk more about ideal gas mixtures. Before I do that, I want to differentiate the huge difference that we have between an ideal mixture and an ideal gas. So far in the last couple of classes, I've been talking a lot about ideal mixtures, and this is typically in the context of liquids. So I've been talking about partial molar volumes, like when you mix water and ethanol together, and so forth. For an ideal mixture, the assumption is that the interaction between the molecules are the same as if the molecules were interacting with other molecules of the same type. So interactions between molecules of different species are very similar, to interactions between molecules of the same species. So remember my analogy that I took from the Dom and Visco textbook of a party with chemical engineers and mechanical engineers. Those interactions between the chemical and mechanical engineers are going to look very similar to the interactions of chemical engineers with other chemical engineers. But on the other hand, so I guess I'll start by saying that the mechanical chemical engineer mixture is an ideal mixture. For the mixture of chemical engineering students with art history students, those interactions are not going to look at all like interactions between chemical engineers with other chemical engineers. So in an ideal mixture, the key is that there's still interactions that are happening between molecules. In contrast, for the ideal gas, the assumption is that there are no interactions at all. Assume no interactions at all. So this is like the quarantine lockdown where everybody's just sitting at home and nobody's really having interactions with anybody. Hopefully, you are finding ways to interact with your classmates, by the way, and it doesn't have to be so isolating, even though we're doing the semester on Zoom online. So how do these get reconciled? How can I go about modeling a mixture of ideal gas? Well, if I'm modeling a mixture of ideal gas, it's ideal in the sense of the gas is ideal in that there are no interactions at all. Right, so if I don't have any interactions at all, then I have to think about it differently than if I did because it was a liquid. So recall the following relationships from MEB. Remember, I could define the partial pressure of a component in an ideal gas mixture as P sub I, and I said that P sub I was equal to YIP. This is from MEB, where PI is the partial pressure, Yi is the mole fraction of I in the vapor phase. And also remember that this is different than in the last couple of videos I've been using X for the mole fractions. That was because that was the liquid phase. So I like to use X's for mole fractions of liquids, Y's for mole fractions of vapors. And this big P is the total pressure. And because we are assuming an ideal gas, I'm going to say that P is equal to RT over V, such that my partial pressure I can rewrite as YI RT divided by V. So for an ideal gas mixture, I'm going to define all of the thermodynamic properties or the partial molar properties as just the sum of all of the pure component properties because there are no interactions anyway. So we're going to use the ideal gas as the baseline for building the model. Or said differently, we can say that the partial property, so partial molar property, where again theta is any thermodynamic property, as a function of temperature, pressure, and mole fraction is simply equal to the molar thermodynamic property. Molar thermo property as a function of temperature and the partial pressure. And also I need to write this down that the sum of all the partial pressures equals the total pressure. which should make sense because the sum of all the mole fractions must equal 1. So therefore, when you apply this relationship to this equation, you should see that those are all becoming the same thing. All right, so for different thermodynamic properties, this equation looks a little bit different. We'll start with enthalpy and internal energy. And before I go on, go ahead and add subscripts onto these, just to denote that it's for an ideal gas, such that we don't ever forget. So the enthalpy for an ideal gas mixture can be written as the partial molar enthalpy for an ideal gas as a function of T and P must be equal to the molar enthalpy of that same component as a function of temperature and partial pressure. And because partial pressure, whether you use partial pressure or total pressure for an ideal gas doesn't matter. Remember, because enthalpy is not a function of pressure for an ideal gas. Equals HIIG of T and P. And we say that this relationship is because H is not H of P for an ideal gas. So it does not matter which pressure we use there. We could have kept it as partial pressure. It does not matter. Same thing for internal energy. Partial molar internal energy of component I in the ideal state as a function of T and P is equal to the molar internal energy as a function of temperature and partial pressure, which is equal to the molar internal energy as a function of temperature and pressure for the same reason. So U is not a function of P for an ideal gas either. Okay, what about entropy and molar Gibbs energy? So for entropy and molar Gibbs energy, remember entropy is a little bit strange. Even though there's no interaction between the molecules, if you mix them, that is a spontaneous process and they can never undo themselves. So we do have to have a change in entropy. So for entropy, I can start by saying that the partial molar entropy for an ideal gas for component I at some temperature and pressure is equal to the molar entropy of that component of the ideal gas at some temperature and some partial pressure. But this is not going to be equal to the molar entropy of an ideal gas for temperature and total pressure. So this is because S equals S of P. So entropy is a function of pressure, even for an ideal gas. And because entropy depends on pressure for an ideal gas, we next need to ask ourselves, how does a change in pressure in P affect S? All right, so go back to our thermo roots. We want to express what we want to know in terms of something that we do know. So want to know ds, and we express it as a function of P. Just for sake of clarity, I'm going to say that S is a function of T and P, which is true, by the way, but we're just looking at the change in pressure here. So I can say that S is equal to ds dt at constant P dt plus ds dP at constant T dP. Now, if you want a practice problem, see if you can go from this, do this derivation and prove to yourself that this following relationship is true. So if you do this derivation and you work out what the change in enthalpy for an ideal gas of component I, you should get it equal to the integral of Cp over T. This is Cp star for component I. Also at a certain pressure too. So Cp, constant pressure heat capacity at a certain pressure. Remember, even though it's not a function of, it is a function of pressure even though pressure is constant. dt minus R integral of dP over P. So again, use your calculus tricks and see if you can get to this bottom equation by manipulating the equation above. And now if I integrate this expression, So I want to figure out what the change in ds for an ideal gas as I go from P1 to P2, or in other words, if I go from partial pressure to total pressure, then whatever the dt is, I know I have a dt term, but because I'm not changing t, so if t is constant here, this dt term can go away. Again, I'm just looking at how the change in pressure affects entropy. Then I'm left with r times the integral of 1 over p dp, and this is equal to minus r ln of p, and rewritten for the limits of integration, which are pi to p, is p divided by pi. And then I can rewrite p as the mole fraction times the total pressure. Rewrite the partial pressure as the mole fraction times the total pressure. And then the total pressures cancel out, and I've got ln of 1 over yi. And if I take the reciprocal of inside the ln, then a negative comes out front. So I can rewrite this further and say that this is r ln of yi. So reciprocal here, again, because I have ln of 1 over y, that is equal to minus ln of y by a property of logarithms. And that allows me to get to this final step. So if I finish out and write this neater, I can say that the partial molar entropy of an ideal gas for component I at some T and P is equal to the molar entropy of component I for the ideal gas at some T and partial pressure. And that is equal to the molar entropy for an ideal gas at T and P, and then I have to add this term plus ln, r ln of y. And I missed a minus because I forgot to integrate this left-hand side. This left-hand side is not, it's sneaky. It's SIIG evaluated from P to PI. So this is equal to the molar entropy of component I for an ideal gas at T and P minus SI for an ideal gas at T and PI. So if I want to figure out what SIG for T and PI is, then I have to take these things over to the other side. So I have to evaluate this a little bit more carefully. So this is my full equation, r ln of yi. And what I'm doing here is I'm solving for this middle term, SI for an ideal gas at T and PI, because that's what I have there. So this is equal to SI for an ideal gas at T and P minus r ln of y, because this term came over to the other side. So this is my final expression for entropy. This is partial molar entropy for an ideal gas. Partial molar entropy of component I in an ideal gas mixture. Okay, the partial molar Gibbs free energy is a very similar derivation. And I'm just going to give it to you. Again, you can, I encourage you to try to derive this yourself. So see if you can get here doing the derivation. So follow similar steps to for entropy. So partial molar Gibbs energy of component I as a function of T and P is equal to the molar Gibbs energy for an ideal gas at T and partial pressure. And that is equal to molar Gibbs for an ideal gas at T and P plus RT ln of y. All right, one last variable to solve, and this one is volume. And volume is a little bit trickier. This is why volume is a little bit trickier for an ideal gas mixture. Let's take the definition of partial molar volume. So partial molar volume for an ideal gas mixture is just defined mathematically as the partial derivative of the total volume for an ideal gas as a function of the change of moles of species I at constant Tp and Nj, where J is not equal to I. All right, we know what molar volume for an ideal gas is. That's just RT over P. All right, so we can take the derivative of that. And if T and P are all constants, then we can factor RT and P all out of the derivative. And my change, so the partial derivative of the total number of moles with respect to the moles of species I is just 1. So therefore, this partial molar volume, VI for an ideal gas, is equal to RT times the partial derivative of N with respect to Ni, which is 1. So it's just RT over P. All right, but we also know that because this expression is true, we could say that this is equal to the molar volume of an ideal gas. So a very subtle difference here, and it's because this subscript I. So what this says is the molar volume of species I for an ideal gas at some certain temperature and pressure is equal to the total volume of an ideal gas at the same temperature and pressure if all the molecules in the mixture were one component. And that makes sense, right? The ideal gas, PV equals nRT, holds no matter what the gas is. So as long as I have the same constant moles, temperature, and pressure, my molar volume must stay the same. Or said another way, if my pressure and temperature are the same, then my molar volume must also be the same. So what are the implications of this? So taking this a step further, we might think that we can write the following equation, where the partial molar volume of component I for an ideal gas at a certain temperature and pressure is equal to the molar volume of component I of an ideal gas at a certain T and partial pressure. But this equation cannot be true because the pressures are different. So if I have the same number of moles of component I but a different pressure, I cannot say that these things are equal. So this equation does not work, and I have to have an alternative. So for volume, what you have to say is the molar volume of an ideal gas at some T and P is equal to, you do it in a way that you assume it's like an ideal mixture. So you take a weighted average of the mole fractions. So Y1 times partial molar volume for component 1 of an ideal gas at T and P plus Y2 partial molar volume of component 2 for an ideal gas. And then you could also write, this is an equivalent way to state it, Y1 times molar volume 1 of an ideal gas, T and P, plus Y2 molar volume for an ideal gas at T and P. So this is another way of saying that volumes for ideal gases are always additive. And this is because, again, there's no interactions between the molecules. Volume for ideal gas mixtures are always additive. All right, this was a lot of stuff. I know it's very theoretical. I maybe didn't do the best job explaining it, so I'm anticipating a lot of questions on Wednesday for next time. I need to finish out this thought. Always additive, and that is the conclusion for this video.